Hello everyone, welcome back to this class. In this class, we will discuss about aircraft stability and control. For today class, we will focus on aircraft longitudinal stability and control, and then in upcoming classes, we will discuss about the lateral stability and control as well as the directional stability and control. So I already given you the definition of the what do you mean by static stability, what do you mean by dynamic stability, but here we will do the some detailing of aircraft longitudinal stability and control. So first, the terms is appearing longitudinal, right? So first you understand what do you mean by the longitudinal. So this is the aircraft, consider this three axis, okay? So my this finger is pointing towards this direction, right? So this is positive x, and this finger is positive y, and my thumb is pointing downward. So this is the axis system. So if the aircraft rotates about the y axis like this, and it can translate x direction and z direction, that is nothing but longitudinal motion. So in stability, particularly in longitudinal, what will happen if you disturb from an equilibrium position? What is the equilibrium position? Where the net forces are zero, that means forces and moments are balanced. So you are not having any net force to accelerate or net moment to rotate, and some disturbance comes, for example, through atmosphere also it can come gust, okay, and you can deflect the elevator up and down to disturb the aircraft. So if it is disturbed from the equilibrium position, if it has a tendency to return back to its original position, this you define as a static stability, okay. So at an instant you are talking about static stability, but it will take some time to come back to this original position. Now you define as a dynamic stability, okay. So what are the parameter associated with this, how this disturbance is created, and how the aircraft is pitching up or pitching down, and who is countering to come back to this original position. All the things will discuss about the stability, longitudinal stability in this class. And also stability, along with stability you have a control also. That means every time you can control your aircraft in all three axes, right? Roll, pitch and yaw axis, right? Okay. So here the control is elevator. When you deflect the elevator up, your aircraft will go up, and will deflect the elevator down, the aircraft will go down, right? So stability and control are closely related, and unstable system is also controllable, and stable system is also controllable. For example, this aircraft is stable, but quad rotor is unstable, but control quad rotor is flying, right? Why? Because it is controllable. And for example, simple pendulum, if you disturb from the some equilibrium position, this is the equilibrium position. If you disturb, it will come back to the original position, right? Okay, but you can control this moment also, right? So a stable system also, and you can control also. But consider this scenario uh, when you have done this opposite inverted pendulum. So in that, if you leave this pendulum, immediately it will fall. But if you move this in your hand like this, it will never fall. It means something moving platform, if you associate, if you move this pendulum or with your hand only, it will never stop. But because you are controlling, right? So okay. So here we will discuss about the longitudinal stability. So in longitudinal stability, you can say that there is a wing, there is a tail. So all the story will lie in this tail and wing only, right? And fuselage, okay. But you will see fuselage contribution is very less, okay. So we will draw simply tail and wing here. So this is x-axis, what I have shown to you, right? Okay. And you are seeing just from the side, so you can see this is the my wing. Just I am drawing one line, okay, and this is tail, okay. So now this initially what you are angle you are giving with the fuselage reference line, that is known as a wing incidence angle, okay. So if this is a free stream velocity, so that angle, the what angle chord is making with this free stream velocity will be the, this angle will be the alpha w, right? So alpha fuselage reference line uh, alpha FRL, you may denote that as alpha w minus IW, okay. This is the angle, okay. Now some initial setting you are giving, like a wing you have given initial setting, right? So you can give the tail for initial setting. Later we will come to know that whether this IT will be negative or positive in order to make the system stable, or to trim the aircraft at a positive angle of attack, okay. So in this diagram also you can draw the pilot to this uh, opposite to this free stream velocity, you may draw the drag, and perpendicular to that you can draw the lift, okay, whatever you can do. And here if you draw this parallel line V, same line I am drawing here, right? But here will be some downwash angle, because downwash coming from the wing will affect on the tail by this angle sigma, okay. So this is the typical representation of a wing and tail angles and all that. I want to give the feel for that, how the uh, wing and tail has been placed, and what is the angle relation, and what is the angle at the tail. Angle at the tail will be alpha t. For example, this angle will be same, alpha w minus IW, and this is decreased by some amount, and then due to downwash, and then you add IT. So this is the angle relation, okay. If you remove IT and downwash, you will see this angle of attack and this angle of attack will be same, okay. That means your wing downwash is not affecting at all. So why I have given the angle difference, because very important. In later part we will see that this angle is important to derive the expression for a CM naught, CM alpha. This angle relation will make sense also when you derive the uh, expression, okay. If this angle is very small, for example, let's say if alpha w minus IW is very small, then I can draw like this, okay. Now I will draw the wing, because since angle is very small, so I am not tilting, okay. And this is tail, okay. I can give the lecture name also, aircraft longitudinal stability and control, okay. So first I will consider wing alone, okay. Wing alone, okay. Later I will put tail and will combine together, okay. So already I told you alpha w minus IW is very small, and your CG is lying somewhere on this axis. In this axis, fixed reference line, CG is lying. That means you don't have any ZCG, right? Is small first, and ZCG 0. Okay, and also since you will have a drag, okay, so drag can also produce some moment about CG, right? So you consider your CL will be much greater than CD. Okay, so you will not see, that means you will not see any drag effect on the expression. Okay, there will be no drag contribution at all if you are in this, and this is very fair assumption if you fly at a low angle of attack. Okay, now so this is my leading edge and this is my trailing edge, and this is C by 4. This is C by 4 line. This at this point lift will act, right? LW, and from the wing, since we have to define one reference point, right? So from the leading edge we will measure all the distance, right? So I am denoting as a XAC of a wing. Okay, and now CG is here. So this distance I will denote XCG. Okay, and this is CG. Okay, so now moment you can write about CG, what? MCG is MAC of the wing. That means there will be movement about aerodynamic center due to airfoil. For example, if you have a symmetric airfoil, so net upward pressure and downward pressure act at the same point, right? So there will be no aerodynamic moment about the no moment about the aerodynamic center, right? For example, let's say the net downward pressure and this pressure P upper, lower and P upper will act at the same point, right? So will not have any pair which can produce the moment. Okay, and if you use the cambered airfoil, you will have, right, you will have this pair. So that is how MAC is coming. It is coming from the airfoil. If it is symmetrical, you don't have any pair, and if you have a pair, it will produce some moment, right? Okay, so this is all about concept of MAC. Then you have a lift. What is the distance from this lift line and CG? Lift line and CG is LW XCG minus XAC of a wing. No doubt, right? Simple, right? I will write again here. Okay, MCG will be like MAC wing Now you can divide this equation by half rho v square s c bar, half rho v square s c bar, and same half rho v square SC bar. Okay. And this MCG you can write half rho v square SC bar CM CG wing. Okay. And half rho v square SC bar. And this you write half rho v square SC bar CM AC of a wing, and half rho v square SC bar, and this left you can write half rho v square SCL, and this half rho v square SC bar and XCG minus XAC. So now half rho v square SC bar you can cancel. Okay. So now, and half rho square S C bar cancel here also. Half rho square S you can cancel. C will remain. Okay, so you can write CMCG wing, CMAC wing, CL XCG by C minus XAC by C. So with the common sense, can you tell me how this, if you disturb the aircraft, it will try to counter, right? So as long as you are increasing the angle of attack, your CM is going down, right? So how the graph will look like if you plot the CM versus alpha? CM CG CMAC wing plus CL XCG by C bar XAC by C bar. Okay. Now CMCG you can write as a CMAC of the wing, and then CL will be CL naught plus CL alpha into alpha, and XCG by C minus XC by C. Okay. Please, already I explained to you what is CL naught and CL alpha. You may revise also. Okay. So if the airfoil is camber, you will be having the curve like this, and this is a alpha, this is a CL. So when the angle of attack is 0, so whatever the CL you are having, this is our CL naught. Okay, and the slope is CL alpha. So it is similar to y equal to mx plus c, where intercept is CL naught and m is CL alpha, right? Now this you may further write Cm naught of the wing plus Cm alpha of the wing into alpha. Okay, alpha is the angle of attack. Okay, Cm, because like a CL equal to CL naught plus CL alpha into alpha, one term CL naught is coming and one term is CL alpha is coming. Okay, so one is directly associated with this alpha, CL alpha into alpha, and one is CL naught. Okay, so that is how you can write Cm also, Cm naught plus Cm alpha into alpha. Okay, CL naught XCG by C bar minus XAC by XAC of the wing, you should write C bar. C bar is a mean aerodynamic point. Okay, and CL alpha XCG by C minus XAC. Okay, so now you compare these two. what you will get? If you compare, Cm naught of the wing will be this part, this part, this part. Okay? And Cm alpha of the wing will be this part. Okay? Okay? Any doubt up to this? See, it is a simple. Just force equal to moment equal to force into distance. So what will be the Cm naught of the wing? It is Cmac of the wing, Cl naught of the wing, and xcg by c bar and xac by c bar. Okay, xac of the wing. And Cm alpha of the wing, Cl alpha of the wing, xcg by c bar minus xac wing by c bar. Okay. Since we are dealing with wing only, so you may put W here. Okay. Cl alpha of the same them to avoid any confusion. Put everywhere. Okay. Wherever it is necessary. Okay. Cl, you write Cl of the wing also. Okay. Everything we are dealing with wing only, right? Cl of the wing. Okay. Everything we are dealing with wing. Okay. Okay. All right. So now, can you tell me this is a positive or negative? This value positive, right? Positive. That means observation okay, Cm alpha W. You told, right? And I also agree with the same. It is positive. So consider this aircraft. I am increasing the angle of attack and moment is also increasing. That means diverging, right? If you increase the angle of attack, let's say this is having some angle of attack. Okay. This is a chord. You may draw this as a some this is a chord. Okay. Or leading edge, trailing edge, astern. This is a chord. C bar, and this is a velocity vector. This is the angle of attack alpha W. Okay. And okay. Now, when you increase the angle of attack, your lift will increase. The moment above CG is will also increase. तो एयरक्राफ्ट क्या होगा? पिचअप होता जाएगा ना, पर स्टेबिलिटी के हिसाब से तो वापस आना चाहिए. इट हैज टू रिटर्न टू द ओरिजिनल पोजीशन. दैट मींस सीएम अल्फा साइन शुड बी नेगेटिव. ठीक है. अब देखो इस क्वेश्चन को. what you can do to make CM alpha नेगेटिव. आप CG को एरोडायनामिक सेंटर के आगे ले आओ. CG should be ahead of the aerodynamic center. So अब आप खुद सोचो, ये विंग बना है, अब इसका मास होगा, बाई शेप देख करके देख लेगा कि भाई यहां पे तो CG नहीं आ सकता आसपास. इसके लिए तुम खूब सारा यू विल पुट लॉट ऑफ मास हेयर in order to bring the CG ahead of the aerodynamic center. For example, but it is not a making sense, right? Or another way, I already told that you can give the sweep back to make aerodynamic center to move the aerodynamic center in this direction. Okay. So CG should be anyway CG should be ahead of the aerodynamic center, not behind of the aerodynamic center. If it is behind, it is unstable case. But here we cannot do, right? So what we will do? We will put the tail in order to move this aerodynamic center behind the CG. Okay. So when you draw this graph, you will, and one more important part. This is Cm naught contribution. So Cm naught, see, Cmac of the wing is always negative as long as it is a positive cambered airfoil is concerned, and Cl naught is positive, and this value is also positive. So overall, even if this value negative, the overall value of a Cm naught will come negative, because this value Cl naught of the wing, this value will be larger than compared to this Cmac of the wing alone. Okay. When you select the airfoil, you may select, you can get the feel for this Cmac value. It can come minus 0.08, minus 0.02. If it is a highly cambered, this value will be more. If it is a low camber, obviously if it is symmetrical, that means zero camber, this value have a 0. And consider the symmetrical airfoil. If Cmac is 0, this Cl naught will be Cl naught of the wing will also be 0, right? So 0, 0, all is 0, right? So Cm naught is 0. So Cm naught is 0 means you cannot trim the aircraft at a 0 angle of attack. That is why in aerobatic aircraft you use the symmetrical airfoil. You can perform, see, symmetrical airfoil generally used to perform the maneuvers, right? Aggressive maneuvers. Here you will give the initial incidence, because you cannot fly at a 0 angle of attack. So Cm naught will tell you at what angle of attack you can fly. For example, if Cm naught is positive, you can fly at a positive angle of attack. Okay, you may draw the graph also. For example, like if I am drawing the graph like this, for a this is a Cm and this is a alpha. Okay, so one graph is this. Okay, and another graph is this. In both the cases, which one is the stable case and which one is the unstable case? First is stable case and second is unstable case. Okay, that is clear, right, from the graph. At alpha equal to 0, this part is a Cm naught, right? Okay, so let's say this is a 0 angle of attack and this is 3-degree angle of attack. So 3-degree angle of attack you can fly, right? 4-degree you can fly, 5-degree, 6-degree, at odd degree you can fly, right? So that is the significance of Cm naught. Okay, you can fly, you can trim the aircraft as a positive angle of attack. Okay, you can make Cm equal to 0 at this angle of attack. Okay,